Thank you very much for the introduction. It's really a pleasure and an honor to be invited to give this keynote lecture, and it's really a pity that I cannot be there with you, but I hope that you will enjoy this presentation, and I will anyway be available to answer questions at the end. So this work is on explaining and controlling turbulent flows through deep learning. This is research funded by the ERC, the European Research Council. And I would like to start by acknowledging some of my collaborators and contributors who have really made this possible. These are only some of my closest collaborators. There are many more students, postdocs, researchers, and friends who have really made all of this possible. Also, we can motivate a little bit the work that I'm going to be talking about today by looking at a typical airliner. This is an Airbus A320. If we look at the different contributors to the total drag, what we see is that about 50% of the drag comes from friction. So that's turbulent boundary layers. And in particular, the boundary layers developing around the curved surfaces on the different parts of the airplane. And about 40% of the total drag comes from the lift-induced component, which happens at the wing tips. So basically, due to the difference between the pressure and the suction side, you have these wing tip vortices, which I will be mentioning briefly later in the presentation. So if we look at turbulent boundary layers with pressure gradients, we can understand more or less 50% of the total drag. And then this additional 40% comes from these wing tip vortices, which are actually quite important as well. So what am I going to be talking about today? I'm going to talk about three different things. And of course, I want to relate the topics that I'm interested in, which has to do with high-performance computing and turbulence on the one hand, and on the other hand, also machine learning and data-driven methods that can be coupled with these challenges that we want to be looking at. So in the first part, I'm going to be talking about our work over the past years on high-fidelity simulations, mostly DNS or slightly coarser DNS on pressure gradient boundary layers and wings. We have produced a lot of very good and high-quality data. Then on the second part, I'm going to be talking about how to analyze that data using explainable deep learning and how we can really learn something new about coherent structures in turbulence with this technology, with explainability. And finally, the part that is a bit more computationally involved in the sense that we had to couple different machine learning libraries and different CFD codes, which kind of connects a bit with the main interest also of this conference. I'm going to be talking about deep reinforcement learning for flow control in the context of turbulence. So let's start with the first part. Let's start by talking about high-fidelity simulations. What I'm going to show you here is actually a DNS. So this is a fully resolved direct numerical simulation of the turbulent flow around an ACA 4412 wind section, Reynolds number 400,000, and angle of attack 5 degrees. This simulation was carried out quite some years ago now. You can see the reference to all the data and statistics in this reference in 2017. What you can see here are basically vortex clusters colored by streamwise velocity, and we are flying around the wing. So close to the train edge, you can see a region of incipient separation. The flow is actually attached on the mean, but there is more than 30% backflow. You can see now how the boundary layer on the suction side is significantly thicker than the one on the pressure side, and there is much more large-scale energy in the outer region due to the effect of the adverse pressure gradient. There is an adverse pressure gradient on the suction side, which produces these effects. And now we're flying on the pressure side, that's the bottom surface of the wing, where you can actually see how these vertical motions look different because they're subjected to a mild favorable pressure gradient, which basically attenuates some of the energy transfer mechanisms in the boundary layer. You can also see now the level of detail that we can achieve on the wake and basically the typical von Karman type of shedding in the wake of the wing. So this is just an example, and again, the simulation is few years old. I will be showing something more recent soon, but just to illustrate the type of high quality data that we can produce nowadays. And of course, we want to understand a bit what happens on the top of the wing, on the suction side. and that's basically exposed to a quite strong average pressure gradient. At the top, you have a flat plate boundary layer where essentially as the streamwise distance increases, the boundary layer develops. And we have progressively a higher Reynolds number with more and more energetic motions in the outer region when there is a zero pressure gradient. So there is no acceleration or deceleration of the flow. So the free stream velocity is constant. But on the bottom panel, I'm showing you what happens when you have an adverse pressure gradient. So basically the pressure is increasing as I move downstream, which means that effectively the wall normal velocity is increased. So we are just having much more convection in the vertical direction. This leads to a significant thickening of the boundary layer and also to two interesting effects. First, we have migration of some of the small-scale energy close to the wall towards the outer region due to that increased wall normal velocity. And then you have also more energetic scales in the outer region due to the increased production there. And that's due to the different shear, which then couples with different Reynolds stresses, basically leading to more local production of turbulent kinetic energy in that outer region. Now, to give you an idea, on the right, I'm showing you in blue the wall normal velocity of a zero pressure gradient boundary layer, and in red of an adverse pressure gradient with a moderate pressure gradient intensity, and the value of the wall normal velocity close to the boundary layer edge is about 4 times larger in the case of the adverse pressure gradient, the APG. So APG effects are closely connected with this wall normal convection, with this vertical velocity that I was mentioning. Now, something that we were very interested in was flow history, right? Because of course, this pressure gradient magnitude changes, and you have different wing geometries and different the fuselage, and you have all these components of the aircraft that are going to have different geometries. They're going to basically introduce different flow history effects, different pressure gradient evolutions. So we're looking at this quantity beta. This is the so-called Rota-Clauser pressure gradient parameter. Is basically the displacement thickness over the wall shear stress times the streamwise pressure gradient. And what I'm showing you here in the big figure is in the vertical axis beta, which is the pressure gradient parameter, the Rota-Clauser pressure gradient parameter, and in the horizontal axis, the friction Reynolds number. This is work, by the way, carried out by Alexandra Bobke quite some years ago also, but still relevant today and perhaps even more relevant due to the new findings that we're having with history effects. The different colors are different cases, different simulations. In red, I'm showing you the wing that I just illustrated with the video. In the wing, the pressure gradient parameter increases very, very quickly, right? So you really reach very, very high values close to the trailing edge of the wing. And the friction Reynolds number at some point starts to decrease. And this is because the adverse pressure gradient increases the thickness of the boundary layer, but it also reduces the friction significantly. So at some point, the reduction in friction is so pronounced that the trend in tau, in the friction Reynolds number, goes down. Now, the rest of cases are pressure gradient boundary layers on flat plates with different evolutions of the free stream velocity, which basically are leading to different evolutions of beta. All of these are in near equilibrium, which means that the outer region is self-similar, and we have an evolution of the free stream velocity following a power law. The orange line gives you a constant beta of 1, and the brown line a constant beta of 2. The other cases have a variable beta, although they are still in near equilibrium. Now, why is it interesting to have constant beta cases? This is because they allow us to define somehow canonical APG conditions in the same way that the zero pressure gradient boundary layer is a widely studied case, and it's a particular case of constant beta boundary layer where beta is equal to 0. Right? So when you have a constant beta of 0, you have a zero pressure gradient case, constant beta of 1, 2, etc. Those are more general APG cases, still with constant beta. And constant beta cases allow us to separate, on the one hand, pressure gradient effects, and on the other, flow history effects. So what I'm showing you here is what happens when we try to match the local pressure gradient and Reynolds number conditions. And so here in point number 2, you can see how the red line and the purple line intersect. They have the same Reynolds number and the same beta, but different flow histories, right? The red line comes from very small values of beta, which increase very quickly, and the purple line basically is a boundary layer that has been exposed to a strong pressure gradient for quite some string-wise development. At the bottom left panel, I'm showing you the inner scale mean velocity profile as a function of the wall normal coordinate, which is in the horizontal axis. The colors correspond to the cases in the top right panel, and in black, I'm showing you the zero pressure gradient boundary layer at the same tau for reference. So one very, let's say, a prominent effect of the APG on the mean flow is the increase of the wake region. So basically, in the final part of the boundary layer, where the velocity reaches kind of constant, not necessarily completely constant, but kind of constant value. That's the inner scale free stream velocity. That's a larger value in APGs than in ZPGs. And that's because you have less friction. So you have less friction, and this is a scale with the friction velocity, that wake becomes more prominent. And though both APGs exhibit a more prominent wake, which is as we expect, but the purple line exhibits an even more prominent wake, which is something kind of interesting because the local friction, Reynolds number, and pressure gradient is the same in both cases. If we look at the right panel, what we have is in black the zero pressure gradient case, and another important effect of pressure gradient effects, of APG effects, is an increase of both the inner and outer peaks of the stringwise velocity fluctuations, which you can see here. These are the Reynolds stresses, and the effect of the flow history, as you can see, is more pronounced in the purple case, because even if both the red and the purple profiles have a quite a strong outer peak, the purple line has a much stronger outer peak than the red one, which indicates that that boundary layer has been exposed to a much stronger APG evolution, which means that the accumulated effect is more prominent. It's interesting because in the near wall region, the peak is the same in both cases, which suggests that small scales react more quickly to the changes in pressure gradient, whereas large scales react more slowly and then more exposed and more sensitive to the upstream evolution of the pressure gradient. So this is a little bit what we can basically show as evidence that flow history is important. It's not about the local pressure gradient or the local Reynolds number, but the upstream evolution of these quantities. And if we look at point number 3, what we can see is that the blue line has been exposed to a slightly different evolution from the brown line, but for quite some, for the final evolution of the domain, the two lines are actually very close. In fact, for 7 boundary layer thicknesses, they are both quite close. It shows that if we look at the statistics, they actually match quite well, the blue and the brown lines. And that shows that it's actually possible to converge to a sort of canonical APG state, in this case with beta 2, even if the upstream history is a bit different, as long as you maintain for quite some stringwise development the same flow history, the same pressure gradient conditions. Again, these are simulations carried out with this particular, in this case, it was a Fourier-Chebyshev code, quite large computations. And this is almost DNS solution, so quite well resolved. How can we really use this knowledge that we are gaining about flow history and different flow cases and evolutions? Well, this is one empirical result, an empirical correlation that we developed also some years ago. You can see the reference at the bottom. What we are doing here is predicting the skin friction curve from any pressure gradient case based on the skin friction curve from zero pressure gradient boundary layers and the shape factor from zero pressure gradient boundary layers. And both the skin friction and the shape factor for ZPGs, they have very well-known correlations. So we can actually use those correlations as our baseline, and then we can correct with the pressure gradient to try to go to the right APG case. And in our case, we use this beta average, which you can see defined here, as a way to encapsulate the upstream history of the boundary layer. So this beta average is just an integral of beta with array theta, with the momentum thickness-based Reynolds number. And what you can see on the left in these lines is the skin friction as a function of the momentum thickness-based Reynolds number for the various cases, where black is the ZPG, red is the wing, and in between you have the rest of APGs. And on the right, the symbols are the predictions of the skin friction based on this empirical formula, which, as you can see, it's actually giving us quite good agreement. So of course, this is just an empirical correlation. One can probably improve and try to get something more sophisticated for more complex cases. But even in the wing, where the history is actually quite non-trivial, no, with quite a complex exponential increase, the predictions are in fact really good. So this is something to maybe inspire more work on being able to assess history effects more effectively. Something that we're also quite interested in is the spectra. So really being able to understand the energetic distribution across scales. This is work by Ramon Pozuelo, which we published in JFM a couple of years ago. This is now a flat plate boundary layer with a constant beta of 1.4, but a much higher Reynolds number. This is a tau of 2000. So this is actually already a quite pronounced scale separation, which allows us to really pinpoint and assess flow history effects. What I'm showing you here in the vertical axis is the inner scale Wall-Normal coordinate, and the horizontal axis, the inner scale span-wise wavelength. So this is the power spectral density in Z for each Wall-Normal location. In black, I'm showing you the spectrum of the zero pressure gradient boundary layer, and in orange, the spectrum, the inner scale pre-multiplied power spectral density in the streamwise direction for the APG. And of course, the near wall region is similar, but there are two main differences. The first one is this kind of shoulder that you can see here. This is a small scale energy in the outer region, which basically comes from the wall-normal convection that I was talking about before. And the second difference is the outer spectral peak, which is also more intense in the case of the APG, again, due to the different shear, which then produces a different production and different Reynolds stresses. So APGs are fundamentally different from ZPGs, at least in this Reynolds number range. We know also that at higher Reynolds numbers, the APG effects are less intense. So there is a certain exploration to be done with a higher Reynolds number regime, but at the moment, this is everything we know, basically. And I promised you that I would talk about the lift-induced drag. So this is another very recent simulation. This is by Siavas Tosi, who was a senior researcher in my group. This is to appear in JFM. And you can see a wingtip. So this is really a wing that is not periodic anymore. It has a rounded wingtip. This is a simulation with a spectral code NEC 5000 based on spectral element methods. This has also adaptive mesh refinement. And you can see here also the vortex clusters identified with the lambda2 criterion and colored by streamless velocity. This is about 1.6 billion grid points. We have a number of cases. So this is a Reynolds number of 200,000 with 5-degree angle of attack, but we have cases at 0, 5, and 10 degrees. And we have the corresponding periodic cases as well. So we can compare the aerodynamic effect of the wingtip vortex. You can actually see the wingtip vortex here quite well and how it essentially pushes down the wake due to the induced rotation that it has. So through that rotation, the wake gets pushed down in such a way that the ability of the wing to extract lift from the flow gets diminished. So you need to increase the angle of attack to get the same lift. And that adds an additional component to the drag. So that's the lift-induced component. Here you can see in a very high level of detail how the wingtip vortex is rolling from the pressure to the suction side. You have a region of local relaminarization due to the strong span-wise pressure gradient that we are introducing with this wingtip vortex. And you can also see how it really impacts the turbulent boundary layers on the section side and the pressure side. This region of inhibited turbulence or kind of relaminarization, it feeds then the wake, which is also quite affected by these changes over here. So basically, this is a state-of-the-art simulation where we can really, again, produce very high quality data with the possibility of then analyzing this in detail and maybe leveraging some of our machine learning models to try to learn something out. So what can we learn? Now that we talked about the quality of the data, I want to look at how we can analyze the data. And to analyze it, the first question that I'm always asking is, what are the most important regions of the flow? What should I be looking at? This is important from the perspective of sensing the flow, but also from the perspective of controlling the flow. And this is a question that, on the one hand, Encirana Jimenez looked at using what is called an intrusive method. So they were basically taking DNS of homogeneous isotropic turbulence. They were introducing different perturbations in that DNS, and then they were rerunning the DNS to see which of those perturbations were growing the most. And then in that way, they could really assess that strain-dominated vortex clusters were the most important regions, basically. Now, an alternative approach was taken by Lozano, Duran, and Arranz, which is based on information theory and causality. In this method, which is non-intrusive, that means that you're not modifying the flow, you need time series, which you can obtain from model decomposition. And then essentially what they do is that they remove the evolution of one of these time series to see how that affects the future predictions of the rest of time series in such a way that you can really assess its the mutual causality relations among those. And of course, the advantage of it being non-intrusive is that you don't change the flow, but you need quite some data to converge this time series, no, in terms of causality. So what we propose is a method based on deep learning, which is intrusive in a surrogate model. So we change the flow, but we change it in a post-processing way, in that surrogate manner, right? This has one advantage, and is that it can be applied in contexts where there is not so much data, like experiments. So you don't need to run DNSs. You can do it with experimental data. And we showed the feasibility of this method based on deep learning on a turbulent channel at a low Reynolds number with 6,000 three-dimensional snapshots. And we start by looking at intense Q events. The intense Q events are defined by this equation that I'm showing you here. These are basically three-dimensional regions of high values of the stringwise and wall normal velocity fluctuations. So these instantaneous values of the fluctuations need to be higher than the RMS of U and the RMS of V multiplied by some function H, which is a hyperbolic Hall threshold. And this function H is decided such that we can maximize the number of extractors. So at the end, we're just looking at three-dimensional volumes of intense Reynolds shear stress. And this work was developed by Andrés Cremades, who is a postdoc in my group. This was published in Nature Communications earlier this year. So all the codes and all the data are available online. So you can just, and also, by the way, about the data sets that I talked about before, all the data is online. So you can just go to the web of my lab, and then you can find everything there. The method based on explainable deep learning has 3 steps. In the first step, we use a three-dimensional unit, which is a computer vision tool, to predict, given the current state of the flow, the future state of the flow. Then we segment the input field, and we look at the Q events there. And then what we do is that we start to remove Q events to really see how the future evolution of this flow field changes, and in such a way that we can try to look at what of those Q events have more importance towards the predictions of the flow fields. And I'll give you more details in just a second. But to kind of understand a bit more the method, we are using these units that I mentioned before. These units are basically three-dimensional convolutional neural networks. So these are deep learning methods. The convolutions are very good because they allow us to exploit spatial patterns in the data. And of course, turbulence, as you can judge by the videos that I showed you before, it's basically relying on and is composed by quite localized spatial information, these coherent motions. No? So there is a lot of spatial patterns to be exploited through convolution filters to be able to improve our predictions. Our input is going to be comprising three-dimensional flow fields. So the three-dimensional flow fields of the U, V, and W fluctuations in the current step. And the output is, again, the three-dimensional flow fields of U, V, and W in a future step. And how far away are these input and output fields? The results that I'm going to be showing today are about 5 viscous times separation between both, but the results don't change between 1 to 10 viscous times. They're basically the same. Now, what I'm showing you at the bottom is a schematic representation of a unit. So you start with your input, you apply a series of convolutions, then after a while you are reducing the resolution with a max pooling layer. So now the fields are coarser. You apply more convolutions, you perform another max pooling layer to reduce the resolution once again. You apply more convolutions, then you do a transpose convolution to go up in resolution for a bit, apply more convolutions, and then a transpose convolution to, again, recover the original resolution and finally complete some additional convolution filters. Now, the name of this network, is the U-net, comes from this U shape, so not so original, perhaps. You start with very high resolution and you lower the resolution for a while, then you recover the original resolution. Perhaps one key feature here is this green arrow that you can see at the top. This green arrow is connecting feature maps from early in the network, so kind of abstract and perhaps simpler features, and more those feature maps are connected with feature maps at the end of the network, which are much more relying on more complicated features from the flow. So it's been shown in computer vision that such combination of feature maps from simpler and complex elements really increases the performance of our neural networks. And this green arrow, this is something called a skip connection, or basically a residual block that we are having. So this is a quite powerful tool in computer vision. And actually, this method allows us to obtain pretty good predictions. So we're predicting the flow field with only 2% relative error, which, again, nowadays we have even better models with less than 1% error, but 2% error is pretty good. I mean, as you can see here, by looking at the streaks in the near wall region, the first row is the DNS, the second one is the U-net prediction, first column is the lower wall, and the upper column is the upper wall. So the right column is the upper wall. You can see that the streaks are very well represented. The streaks are in very good agreement. The statistics, the spectra, everything is actually pretty good. So this is a good surrogate model to play our game of removing extractors and see what happens. And this is what the method looks like. So what we do is that we have our true input field, okay? Now, what we do is that we are going to use this input field with a U-net to perform our prediction that will give us a predicted flow field, and that predicted flow field is going to be compared with the ground truth, with the DNS flow field, and there will be an error, right? The one from the neural network and the one from the DNS will be around 2% error, something like that. Now what I do with my input is that I'm going to remove extractors. I'm going to remove extractor. I'm going to repeat the prediction, which means that I will have another predicted flow field, which I will compare with the DNS, and I will recalculate the error. And then doing that for all extractors, we will come up with a ranking of how much each of the extractors has affected the prediction error that we are getting. And that's ranking is based on what we call the SHAP values, or the importance scores. So those are really the elements that allow us to assess the importance of each of the extractors. And the idea, as you can see here, is that we can use a linear model G for the error between the neural network and the ground truth. And this linear error comprises these Q1, Q2, Qn variables. These are binary variables indicating presence or absence of each of the extractors. And this phi1, phi2, phi-n, these are weighting factors in this linear function, which essentially indicate the relative weight of that extractor towards the error, right? So these are the SHAP values. These are actually the importance scores. These SHAP values are calculated through a square minimization, right? So we just want to minimize the difference between the true error F and the linear model of the error G. And when that difference is minimized, then we can actually obtain the SHAP values, essentially. Now, there are two assumptions here, right? The first one is that we're using a linear model for the error. The question is that a fair assessment in a nonlinear chaotic flow? And the reality is that the difference between f and g squared, so between the real error and the linear model of the error, is of order 10 to the minus 7, where the fluctuations are of order 1, which means that in principle, we have so many extractors that even if we look only at the leading contribution to the error, we don't look at cross-extractor interactions to that error, still is enough, is accurate enough. So that's in principle good. And the second assumption is that we are looking at structures one by one in a case that is, again, chaotic, nonlinear, and complex, right? Is that representative of the physics? Well, the reality is a little bit more complicated because when we remove extractors, we remove them in so-called coalitions. And these coalitions are groups of extractors where I can basically remove and assess the effect of one extractor in different roles. Some of these coalitions include near wall elements, some of the others include outer flow elements. So the role of each extractor is assessed in different contexts. And we have really tested thoroughly the hyperparameters here in terms of how many extractors per coalition, how many coalitions, in such a way that these results are quite robust. So in principle, these two are assumptions that are required from a computational point of view because this problem is intractable to really look at all the possible combinations. But this gives us confidence that we are having quite converged and robust results. And this is also backed up by the computer vision community, which has also extensively used this type of methodology. So let's look at some results. In the vertical axis, I'm showing you the SHAP value, so the importance. In the horizontal axis, I'm showing you the volume of the extractors, and this is the joint PDF. So basically the joint probability density function of importance and size. And in principle, what we can see here is a pretty good correlation. No? So large extractors are more important, which makes sense. And dividing them into the 4 quadrants, the more important ones in turbulence are the blue ones, ejections, and the yellow ones, which are sweeps. No? Ejections is flow going up, and sweeps is flow going down, essentially. What happens if I scale this per unit volume, right? So now in the vertical axis, I'm showing you the importance per unit volume, and in the horizontal axis, the volume of the extractors. And now that correlation is gone. So the largest things, which are in this blue balloon, are not the most important anymore. The most important things are in that red area over here, which are essentially medium-sized ejections. Yeah? So the classical intuition is maybe not fully correct when we look at things per unit volume. What happens with the Reynolds stress? Because, of course, we're looking at Q events. These are regions of intense Reynolds shear stress. And as we can see here, when I represent the importance as a function of the Reynolds shear stress, there is again a pretty good correlation. So naturally, the extractors with highest Reynolds shear stress are also more important. But if I look at the importance per unit volume in the vertical axis as a function of the Reynolds shear stress per unit volume in the horizontal axis, we get something quite interesting. We get 3 different regions. And in region A, the correlation is gone. So for the same Reynolds shear stress, there is a quite broad range of importances. Okay? In region B, I'm having the extractors with the highest Reynolds shear stress, and in region C, the extractors with the highest importance. And when we look at things per unit volume, the traditional intuition is kind of gone. Now the elements, the extractors with the highest Reynolds shear stress, they're not the most important anymore. There's something else. This is something that helps us when we are looking at things with a more objective definition of importance, right? Because the Reynolds shear stress is something that, well, you know, we can see in the mean momentum equation, and obviously it needs to have some relevance. But at the same time, in this way, we are objectively defining regions of importance. Now, we wanted to corroborate this experimentally because I told you at the beginning that this can be used for experiments. So then we interacted with Ivan Manusek's group in the University of Melbourne. And then we wanted to do experiments because, first of all, when you do experiments, typically you have higher Reynolds numbers than in the DNS. So perhaps the most important things at low and high Reynolds numbers are different. So that's one thing to keep in mind. Another reason to do this method on the experiment is because in experiments, you typically have less access to data. You don't have nicely to resolve 3D things. You have, if you're lucky, 2D PIV data, which might lack some information and some resolution. So the question is not what are the most important regions of the flow, but from whatever I can measure, what is the most important? That's the actual question that I want to answer. And in the database from Ivan Marusik's group, this is a towing tank experiment, so a boundary layer that grows in time. We have again 6,000 snapshots, two-dimensional flow fields, time resolve, and the Reynolds number, the friction Reynolds number is over 1,000. So an order of magnitude higher than in the DNS. Okay. What I'm showing you on the left is, as before, the importance as a function of the volume, and the correlation is still there. So it's a pretty good correlation, like in the DNS. The yellow region has become more important, and that means that the sweeps are starting to become progressively more important. That is expected at higher Reynolds numbers, so that's very well known. On the right, I'm showing you the importance per unit volume as a function of the, well, actually, I should say the surface, because these are 2D planes now, so we're looking at the surface of the structures. So the importance per unit surface as a function of the surface. Again, the largest things are not the most important. It's in this red balloon where medium-sized ejections are present, where we have the most important elements. And the same happens with the Reynolds shear stress. So I have also a good correlation between the importance and the Reynolds shear stress, as in the DNS. And when I look on the right panel now, the importance per unit surface as a function of the Reynolds shear stress per unit surface, we again find the three regions, right? In region A, the correlation is gone. In region B, we have the structures with the highest Reynolds shear stress. In region C, we have the structures with the highest importance. Now, you see actually something pretty cool, because like in the DNS, the most important things are not the ones with the highest Reynolds shear stress. In fact, in region C, you can see Q events with very, very low Reynolds shear stress and very, very high importance. So the classical intuition, the classical knowledge is perhaps not fully correct, in this regard, just because it doesn't need to be that, because we think that Reynolds shear stresses are important, they are the most important. Now, wouldn't it be interesting to look at importance point by point and then try to really look at the regions of highest importance to try to assess new coherent structures? Well, that's exactly what we did. So looking at the experimental data from Ivan Marusik, the 2D planes, we use a variant of SHAP called gradient SHAP, which is more computationally efficient, that allowed us to do this for each grid point. The gradient SHAP gives us an importance for each of the fluctuations. So basically, we can define a percolation analysis similar to the one that we did for the Reynolds shear stress, and basically select the regions of highest SHAP, highest importance, and define structures based on those. What I'm showing you at the bottom is in black the Q events, so the classical structures, and in green the SHAP structures, the new ones. And you can see about 70% overlap, which is kind of interesting, right? It's reassuring in the sense that obviously the Q events are important because they contain strong fluctuations, but they don't tell you the whole story. They're only part of the story. The most important regions are something else. They're not just Q events. In fact, if we do this analysis in 3D, the agreement between the Q events and the SHAP structures goes down to only 30%. So something that we need to keep in mind. What I'm showing you now is the analysis in 3D for the DNS data, and these are very, very fresh results, so we're still analyzing them and expanding them. But essentially what I'm showing you in the vertical axis is the wall normal coordinate, in the horizontal axis, the stringwise velocity fluctuations, and these are joint PDF maps, right? So basically, where does the probability density reside when I'm looking at the stringwise velocity fluctuations and different regions of the channel? And the first panel is the SHAP, the second one is the Q events, then the streaks, and then in the last row, the vortex clusters, the vortices, with two different criteria, which basically give us the same, okay? So that's interesting. I mean, now, again, we are looking at three-dimensional regions of importance. Those are our coherent structures. If we look at this in more detail and we compare, now in big, I'm showing you the SHAP distribution of probability, and on the right, in blue, the Q events, in green, the streaks, in red, the vortices. Now, if we look at the SHAP, we have this blue region over here, which corresponds to ejections. This blue region over here, which corresponds to sweeps. That's interesting. But also, this green region here corresponds to low-speed streaks, This green region over here corresponds to high-speed streaks. And there is even a region here with zero fluctuations, which agrees quite well with the vortex clusters. So when you define importance point by point, without any hypothesis, without any preconceived idea, the most important regions, the most important structures are actually, in some places, Q events, in some places, streaks, and in some places, vortices. So all these classical structures that people have been looking at, they were not really wrong. I mean, they were obviously important, but they would not tell you the whole picture. The whole picture is taken when you put all these structures together and their relative importances in different regions of the flow. Okay? And this is super important, not only to understand better turbulence, but to control it and to try to really reduce drag and really control the flow in a way that is efficient. So this is exciting. And the last part of my talk has to do with control. And for the control part, we're going to be using deep reinforcement learning. So in deep reinforcement learning, we have an agent which interacts with an environment. And the environment, in our case, will be as a simulation of our flow. That interaction is through actions, and those actions are basically the flow control that we want to apply on the flow. Those actions will change the state of the flow, and they will also change the reward. And the reward is a measure of the quality of those actions under a certain norm, like drag reduction. Now, the goal is to define a policy pi, which, given the state of the flow, gives us the best actions to take in order to maximize the reward. And this is work in the turbulent channel by Luca Guastoni, who was a postdoc and a PhD student in my group. So you can find the reference here with all the codes and all the data. And if you want a detailed review on reinforcement learning for flow control, there is this article in Physics of Fluids where we really went through all the methods, all the potential, and all the possibilities. So we consider a turbulent minimal channel at arita 180, and also a full channel at arita 180 as our case, basically. And we want to compare with opposition control. In opposition control, what you have is you have in the near wall region with some sensing plane, you want to really sense the fluctuations, the wall normal fluctuations. And then what you want to do is impose at the wall the opposite fluctuations. So you really want to, in a way that is relatively simple, inhibit the presence of those fluctuations through opposing them. And it works with the wall normal velocity. The results are actually pretty good, especially at low Reynolds numbers, and this is going to be our baseline. In our approach, we're going to be using multi-agent reinforcement learning, and this is also documented in this article in Nature Reviews Physics, where we have different regions of my wall. In these different regions, I'm going to have one or more actuators, in this case, one actuator. And the idea, the state will be the extreme-wise and wall normal fluctuations at y plus 15. The reward is the wall shear stress reduction. And all these different sealed environments share the same parameters, right? So we have, in a way, a mechanism for this agent to be trained in parallel many times. And because there is a certain connection of the rewards between the different sealed environments, we can actually have some sort of cooperation between these agents, actually. And of course, the actions are going to be the wall normal velocity that we want to impose at the wall through blowing and suction. Okay. Some results in the minimal channel, we get 43% drag reduction with reinforcement learning, whereas only 26% with opposition control. So we actually outperform significantly the opposition control. If we take the same policy, train in the minimal channel, and deploy it in the full channel, we still have much better results with deep reinforcement learning. So we get 30% drag reduction with reinforcement learning, only 20% with opposition control. And you can see here by looking at the joint PDFs that there is a significant impact of the control on the flow. The vertical axis is the wall normal fluctuation at y plus 15. The horizontal axis is the extreme-wise fluctuation at y plus 15. In the first panel, I'm showing you the joint PDF of both. So in turbulence, the Q2 and Q2 events are dominant, as we saw in the second part of the talk. So the top left and bottom right panels are dominant. If we apply opposition control, the joint PDF gets a bit shrunk, but it's not really changing so much. If we apply DRL in the last panel, you can see a fundamental change in the distribution. So now there is a quite even distribution across fluctuations, which means that the flow is significantly affected. So there is a lot of physics to be learned by using reinforcement learning to really control and understand these flow fields. You can see here that the amount of actuation from the opposition control, it gets progressively lower as the flow gets more and more controlled. And in the bottom panel, I'm showing you the actuation from the reinforcement learning, which is in practice some sort of bang-bang control or two-step control, which is interesting because this is a quite common strategy found in many areas like drone control and in many robotics, which in this particular case of the turbulent channel turns out to be a quite effective control strategy as well. And these are some examples of DRL for flow controlling in a number of configurations. Now we are doing it in turbulent separation bubbles at very high Reynolds numbers, three-dimensional cylinders, relevant air convection. In all these cases, we are fundamentally affecting the characteristics of the flow. So we are really able to have a big impact on the physics in order to devise novel control strategies that were completely unexpected before. So we're really scaling up to progressively more and more challenging flow cases for flow control. Three take-home messages. We are able to perform DNS for quite complex aeronautical flows now. Our main code is called SOLVE, and that's developed together with the Barcelona Supercomputing Center. That's Oriol Lemko's group. So many of these reinforcement learning applications that you can see here are with this very nice spectral element code, which runs on GPUs very efficiently. The SHAP method is allowing us to identify regions of importance in turbulence and to obtain very deep fundamental knowledge of turbulence. And then finally, deep reinforcement learning is really helping us to obtain completely novel and unexpected flow control strategies. All the data and all the codes are available in this repository. So just access this QR code and you can get everything. If you want more information, I have a series of lectures in YouTube, so you can find all the material there. And also my social media if you want to discuss. I'm always happy to collaborate and talk and brainstorm new ideas. So that's all that I have for today, and I will be happy to take your questions.